we're starting chapter 6 now, which gets us into the heart of statistical mechanics. This is the way where we take what happens down at the microscopic scale and we use statistics to take those basic laws of physics and treat how these large numbers of particles behave statistically and come up with the laws of thermodynamics with what we measure, what we observe happening at the macroscopic scale. The key of all of this is that makes life so much easier is called the Boltzmann factor. The Boltzmann factor, which I've got a definition for written up here, is the probability of finding the system in any given microstate, we'll label that with a lowercase s, when the system is in thermal equilibrium with some large reservoir at temperature T. Okay, and why do I talk about the reservoir having a given temperature, not the system? Well, the thing is that the system, let's say that we've got the reservoir here, which is large, and the system here, which might be small. The two of them are insulated from the rest of the universe so that the total energy is conserved, the reservoir and the system together. But the reservoir and the system can exchange energy back and forth over a barrier that separates them. So the total energy is conserved, but the system's energy is not, and the reservoir's energy is not separately. Now, the system, the reservoir certainly has a well-defined temperature. Maybe it's the air in the room, for example. Whereas the system might be so small that it doesn't have a well-defined temperature. Maybe it's a single atom. What's the temperature of an atom, for example? Well, the thing is that temperature is scaled with the average kinetic energy per particle, or more generally the average energy per particle. Maybe we've got rotational energy and so on. What if you have a single particle? What's the average? Well, the average is whatever it is at that moment, but that can change pretty easily as it exchanges energy back and forth. So that's why we talk about the temperature of the reservoir instead. Okay. So the reservoir at least is large, it has a well-defined temperature, T, and it has an energy, U, and I'm going to put a subscript R for the reservoir's properties. Whenever I need to distinguish them from the system's. The system's energy, we'll just use the letter E for energy. Okay. Now, so the Boltzmann factor, we're finding the probability that the system's going to be in some microstate S. Remember the difference between microstates and macrostates. Macrostates are things which we have large-scale measurements like the total energy or the temperature or the volume. The microstate is some specific arrangement of each of the individual particles. What energy does each specific particle have? The macrostate would be, say, the total energy when you add all of those up. Macrostate doesn't care about how that energy is arranged between the first, the second, and the third particles. All it cares about is the total. Okay, so an example of this, I can lay out the hydrogen atom. Okay. Now, for the hydrogen atom, we have here, I've got a kind of quantum mechanics style diagram. I've got the energy of each of the electron orbitals drawn up here. So the ground state has an energy in electron volts, usual way of measuring energy down at this level, of negative 13.6 eV. Why negative? Well, we tend to have if the electron is on the verge of being dissociated from the nucleus, that's zero energy, zero potential energy. Okay, the ground state has an energy of negative 13.6 eV. The first excited state has an energy of negative 3.4 eV. The second excited state, negative 1.5, and so on up. And notice that they get closer and closer together as you go up, which again is given by quantum mechanics. Now, if you look at how many different states there are, individual microstates at each one of these macrostates, well, when you go up, there's one in the ground state. There's one situation that an electron can find itself in. What are the different microstates? What has it got? Well, it's certainly got the same energy, the electron does, but it can have different angular momentum. So there's only one arrangement for that electron, one angular momentum it can have in the ground state. There are more in the first state, and there are many more than that in the second excited state, and so on. So different things it can have, different properties that electron can have when it's in the ground, first, second, and so on states. So when we talk about comparing one microstate with another, what's the probability of it being in, for example, let's call this microstate S1, it's in the ground state. For example, let that be S1. And we could pick any other microstate and label it state S2. That one there. Maybe we're going to compare the relative probabilities of it being in state S2 versus state S1. Okay. Things we need to keep in mind. If the atom is isolated, if the atom is our system in this example, if the atom is isolated, its energy is constant. And remember, the fundamental, let's see here. Well, okay, it comes from the fundamental assumption of statistical mechanics. All microstates of a given energy are equally likely. This is at least a specific application of the fundamental assumption here. All microstates of a given energy are equally likely. So if we fix the atom's energy, don't let it vary, don't put it in contact with the reservoir. Then, let's say it has total energy negative 3.4 electron volts. It could be in this microstate, the electron could be in this state, this state, this state, and this state, with equal probability, no prejudice from one to another. But it can't go up to that, and it can't go down to that, because we've told it the total energy is fixed. But if we allow the atom to be in thermal equilibrium with, in thermal contact, with a reservoir, the atom's energy can change. The energy is not constant of the atom, and all the microstates of a particular energy level are equally likely as each other. But in general, there will be a different probability of it being in a different energy level. Okay, so we're going to find that the probability that the electron is in any given microstate depends on that microstate's energy. And it's equally likely for it to be in any microstate of a given energy. So, our task is, given any two microstates, S1 and S2, pick any two microstates. We want to find an equation for the probability of being in one microstate versus the probability of being in another. And I put S2, capital P, and I'm making a little bit of a swoosh to it to imitate the way the book does it, is probability. So this means the probability of being in state S2, that's not multiplication, it's probability as a function of. Probability of it being in state S2 divided by the probability of it being in state S1. That's what I mean by relative probability. How many times more likely is state S2 than S1? Okay, now, states S2 and S1 have, they've got a name, S1 and S2, so they're labels. We can label them any way we want. They have, and each of them has an energy associated with it, there and there. And each one of them has a probability of the system being found in that state. So we've got main energy, which I'll label like this. Energy as a function of S1, so that's the energy of the S1 state, and probability. There. So, these are labels I'm going to be carrying through. So how do we find an equation for that relative probability? Okay. So we've got to remember the fundamental assumption of statistical mechanics. Often abbreviated STAT-MEC by physics students, that for an isolated system, all accessible microstates are equally probable. All the microstates a system can get into, if it's isolated, are equally probable. Okay, now in the case that I've set up, the system is not isolated. It's connected to a reservoir. But the system and the reservoir together are isolated from the rest of the universe. In fact, if you really wanted to, you could make the reservoir be the entire rest of the universe, assuming it had a well-defined temperature, which the entire universe, to some extent, yeah. Okay, then, all right. So the system plus reservoir is isolated. Therefore, the total energy, system's energy, plus the reservoir's energy is constant. All right. Now, if the system is in microstate S1, then the reservoir, we're not going to say what the state of the reservoir is. It can be a very complicated one. There are many different microstates the reservoir could be in, but all we know is that if the system is in state S1, we know what the system's energy is going to be. We have to know what that is first, usually. Since the total energy is constant, if the system's energy is known, then the reservoir's energy is known. And if the reservoir's energy is known, then it has a certain multiplicity associated with the reservoir's energy. So then, if the system is in a given microstate, the reservoir has some multiplicity. There's a certain number of ways the reservoir can be arranged and still have that energy. So, the reservoir I think we'll have to erase the word multiplicity because I'm running out of chalkboard. So the reservoir has multiplicity omega sub r of S1. Okay? And if the system is in state, microstate S2, the reservoir has multiplicity omega sub r of S2. Good. Now, let's assume, as I did with that hydrogen atom example, that the energy for microstate S2 is greater than the energy for microstate S1. So, Let the energy for microstate S2 be greater than the energy for microstate S1. So what can we say about the reservoir's multiplicities? Well, if the system has more energy when it's in state S2 than S1, then the reservoir has less energy in state when the system's in state S2. Whatever one gains, the other one has to lose. So if the system gets more energy in state S2, the reservoir has less, and the reservoir is a large system, and if it loses energy, its multiplicity also goes down. This goes back to chapter 2, I believe. Okay. Okay, so the reservoir's multiplicity in state S2 is lower than its multiplicity in state S1. Reservoir, note importantly. Okay, and we know or maybe I should say recall, I'll squeeze it in here. The probability of being in some state, the ratio of probabilities is equal to the ratio of multiplicities. Okay. There. I think I've got to lower that just a hair. This goes back to where we introduced multiplicity in, again, I believe, chapter 2. So, the more ways something can be arranged, the more probable, in a given macrostate, the more probable that macrostate is. And so we can say then the multiplicity of the reservoir associated with state S2 is in some state is proportional to the probability of it being in that state. And since the state of the system fixes the multiplicity of the reservoir, we can tie them together this way here. Okay. Now, using the fact that we can get the ratio of probabilities from the ratio of the reservoir's multiplicities, now we've hit on the key on how we're going to do this. Putting that back up there. Now, we'd rather not work with multiplicities. We'd rather work with entropy. So, applying the fact that capital S entropy, notice I've been using lowercase s with no serifs for the microstate, is k log omega. Let's apply that here and here. So what I need then is, I need to take the natural log of both sides. Oh, wait, no, I'm not going to do that. I'll just go more quickly. I've already got this here, so omega is E. Let's see, if I divide both sides by k, then I've got S over k is natural log of omega, exponentiate both sides. So omega is e to the s over k. And this ratio of probabilities is a ratio of exponentials of multiplicities. So, Again, note how I'm carefully writing entropy as a capital S with a serif. Entropy of the reservoir in state S2 divided by Boltzmann's constant in the exponent over e to the entropy of the reservoir in state S1 divided by Boltzmann's constant. Okay? It's a little bit of a mess, a ratio of two exponentials. But remember, if I've got the same base here, whatever the mathematical term is, e in this case, e to the this divided by e to the that is simply e to the one in the numerator minus denominator. Not wording that way. Well, nevertheless, it's this here. E to the this exponent minus that exponent. Let's see, I can factor out a 1 over k right off the bat. I use the square brackets there because I have parentheses inside. Now the nice thing. I've got this as a difference in entropy. I've got the difference between the reservoir, oops, that's a reservoir. The reservoir's entropy when the system's in state S2 versus the system being in state S1. Change in reservoir's entropy. Well, if the system goes from microstate S2 to S1, for example, or S1 to S2, I guess we've got delta, final minus initial. The system is very small compared to the reservoir as we set it up. That means that maybe that's a big change for the system, percentage-wise, but it's a very tiny change for the reservoir. And that means that delta S sub r, change in the reservoir's entropy, is very, very small. And we can use the infinitesimal change, the differential. And therefore, the change in the reservoir's energy, delta U sub r, will also be infinitesimal, du sub r. Okay. Now, I've still got this is in terms of the ratio of probabilities. Let me take care of this, or this exponent first. And then we'll put that back into the equation for the ratio of probabilities. Okay. So if I take the thermodynamic identity, I want to get it in terms of energy, after all, ultimately. So the fact that du is tied together with ds in the thermodynamic identity means that I can use that to transform this change of entropy into a change of energy, which I'm more interested in. Thermal ID, there we go, nice abbreviation for it. So, for the reservoir, du sub r, so du is TdS minus PdV plus mu dN. And I'm subscripting all of this with the reservoir, except for temperature, which I'm wanting to apply that to the system as well, to the extent I can even talk about its temperature. No, I guess that the state variables like temperature and pressure and so on, if the reservoirs is known, the system should be known. Maybe that's why I don't need to subscript it. Okay. In this case, log that in, something you should know. In this case, the system is not changing, and the reservoir, therefore, is also not changing the number of particles. So, the last term is 0. There's no change in number. PDV. In practice, this term, PDV, is much less than the change in the energy. Therefore, I can ignore this term here. And I'm left with just du sub r equals TdS sub r. Or, I want ds, that'd be 1 over t du. There we go. All right. So, what I came to it was, the ratio of probabilities is equal to the exponential of, that's change in the reservoir's entropy, that's delta S, which in this case is, well, in the case we've set it up so that that's very small, so it's ds sub r. And the thermodynamic identity tells us that that change is equal to, roughly, 1 over the temperature du, change in energy. Okay. So, I'm trying to think how I should space this all out here. I'll try to do it all on one board. So I want my ds, let's see, ds is the change in the reservoir's entropy. So let's expand this. No, I don't need to. I've already told you that's ds sub r. So that is 1 over t du. Du is the change in the reservoir's, du sub r is the change in the reservoir's energy. So the reservoir's energy, so final minus initial, S2 minus S1. Reservoir's energy when the system is in state S2 minus the reservoir's energy when the system is in state S1, but whatever, because the total energy is considered, whatever energy the system gains, the reservoir loses. Whatever the reservoir gains, the system loses. Which means that the change in the reservoir's energy is equal to negative of the change in the system's energy. Let's see if I wanted to put it as, I think I should write that for the system. It may be a fairly large change percentage-wise. So I should write that delta U sub r is equal to negative delta E. Whatever the reservoir gains, the system loses, negative sign. Okay, so that means I've got an overall negative sign if I put this energy change in terms of the system. So I'm going to have negative 1 over t, bracket E, system's energy, in state S2, keep the order the same and put an overall negative sign, yes, minus capital E of S1. Phew. And that's what entropy of the reservoir S2 minus entropy of the reservoir S1 is equal to this. Phew. Okay. I'll put this together now. I've already run through a whole piece of chalk with that. Okay, so I've got that exponent E raised to, it had been raised to delta S sub r over K. Now it's raised to negative 1 over T delta E over K. So, make sure this is visible here. Okay. E to the negative capital E of S2 minus, I'm going to ignore that overall negative sign for now, minus E of S1 all over KT, and there's an overall negative sign out front here. Maybe I should put all this in brackets like that. That's the best way. Okay. Now, let me undo what I did in deriving to this point. A number raised to a difference is the ratio of this to the first divided by this to the second. So, I can break this back into a ratio. So I've got e to the negative energy of S2 over KT divided by e to the negative energy of S1 over KT. Okay, now this is still a ratio of probabilities. Why don't I get all of the S2s together on one side and all the S1s on the other? So I cross multiply. This is the really clever part. I like this. So, let's see here. If the S2s now are in the numerator, the S1s in the denominator. So if I divide both sides by this, and I multiply both sides by this, let's say multiply both sides by that. Okay, what I come up with is probability of state S2 over e to the minus energy of state S2. It's supposed to be over KT there, it's hard to read, equals probability of system being in state S1 divided by e to the negative energy of S1 over KT again. And that sort of semi-cursive K is going to be the death of me, apparently. All right. So why does that matter? There. The left-hand side depends on S2, numerator and denominator both. It does not depend on anything to do with S1. This ratio does not depend on what S1 is. But if you take a look here, the right-hand side depends only on S1 and its properties. It does not depend on anything to do with S2. Yet the ratio is the same no matter which microstate we had picked. This ratio would be the same for every microstate. So that means, now I'm going to zoom back out a little bit. In some way. That means that the probability of any given microstate, I'll just call S in general now, divided by e to the minus energy of that microstate over KT must be the same for all microstates, S, no matter which S we choose. So that means that this is equal to some constant, which is determined by the structure of the system. Now, we're going to call that constant 1 over capital Z. And Z is, I'm going to get to that next, it's called the partition function. It determines how energy is partitioned up among the microstates of the system. Okay. That means, how we find Z is the next section. That means that we get this really useful formula. If I want to find the probability of the system being in a state S, microstate S, I multiply both sides by this exponential, and I get 1 over the partition function, capital Z, times, let's say, scratch here, ignore that, e to the minus energy of the microstate S over kT, Boltzmann's constant, times the temperature of the reservoir. This is the most useful function in all of statistical mechanics. I'll let you gaze upon it in wonder here. Very, very, very important. Because if you know about the structure of the system and can find the partition function, you will know the probability of the system being in any microstate. And those probabilities determine a lot about how the thing works. So, clearly, our next task is to find out how to calculate the partition function. Everything's easy once we've got that. Okay. The partition function, which is a capital Z, by the way, don't make the mistake I did some time back and use that kind of fancy physics and occasionally European style Z with a cross through it there. It's sometimes used in physics and maybe mathematics to distinguish a Z from a 2. There is a different function called the grand canonical grand partition function. Anyway, or the Gibbs partition function, whatever, which uses that cross through it, so don't do that. Not that we're likely to begin with. Okay. Recall the definition of the equation for the probability. 1 over the partition function times e to the minus energy, state S, over kT. Now, one thing I should have mentioned before, this here, that exponential, is called a Boltzmann factor. For state S. The Boltzmann factor tells you the relative probability of the system being in that state, not the absolute probability. You can't put a percentage on it because you need to know the partition function for that. But if you just know the Boltzmann factor, taking a ratio of two Boltzmann factors gives you the ratio of their states' probabilities. Okay, and now we're going to find the partition function. Spell it. To calculate Z, we're going to start off remembering that the system must be in some state. There's a 100% probability of it being in some state or another. We don't know which one of them. So, 100% probability is a probability of 1. When we're dealing with probabilities, usually you're dealing with a fraction rather than a percentage. So, 100% probability is a probability of 1. The probability of it being in one of all of the states there is equal to the sum then over all the microstates of all of these probabilities. So this is a way of saying that if you add up the probability of it being in state S1 plus the probability of being in state S2, S3, and so on like that, and you go over all the possible microstates, probabilities have to add up to 100%, or 1. So add it up for every state, its probability. Adds up to 100%. This is called a normalization condition, by the way. And in quantum mechanics, that's done, this is a normal thing to do. Normalization is normal. All right. So, let's see here. We put in for the probability, we put in this equation here. So, probability is 1 over z times the Boltzmann factor. So far, so good. The Boltzmann factor does not depend on which state you're in. It's a constant. Since it's a constant, it's the same for every one of these terms in the sum, and so we can pull it outside the summation. So, again, we've now got a sum over all the microstates S of their Boltzmann factors, their relative probabilities. If I want to solve for Z, I multiply both sides by Z, and I come up with which is very nice because this tells us that the partition function, which is a very important thing for describing a system, it's nothing more than the sum of all of the system's Boltzmann factors for every one of its microstates. Z does not depend on any one microstate, but it does depend on the temperature. See that this temperature comes into every term here. So what the Boltzmann, what the partition function for the system is, depends on that. Okay. Let's see here. Things that I need to mention. Let me get myself a little more space. Okay. Let's say we pick a state S1, our first microstate, however we want to label it. And if that's the ground state, the lowest energy state that there is, let's say that it has an energy of 0. which is a common way of doing the ground state. Then, so given that, if the energy of the ground state is 0, and there's no energy state lower than that, no microstate has less energy, the Boltzmann factor for that state is e to the minus energy of that state over kT, that's S1, which is, well, that energy is 0, e to the 0 is just 1. This doesn't mean the probability is 1, not 100%, but this is a relative probability. All the other probabilities can be measured relative to this. Then, for all states of higher energies, so for all microstates beyond that, let's see here, for all, there we go. For all energies of microstates greater than the ground state, which is 0, okay? All energies greater than 0, the Boltzmann factor this is a larger number than 0. So we have e to some, well now a negative number, which means it's less than 1. So think about this. The relative probabilities of the higher energy states get smaller and smaller and smaller. The larger the energy of that state is, the lower the probability is of it being in the state. Interesting, isn't it? You're more likely to be in a lower energy state. Those are easier to get to. Nature likes to get to the lowest energy state it can possibly do. Now, but it also depends on temperature. So, as the temperature goes down to 0, you wind up dividing by a very large number here. And negative of a 1 over a very large number, which means this exponent here becomes very, very small, and the Boltzmann factor approaches 0. So as the temperature goes, hold on a second. Yeah, as the temperature goes to 0, how did I say that? I said that backwards. As temperature goes to 0, as you cool it down, you're dividing something over a very small number, which blows up that exponent, but you've got a negative number. That's how it is. And e to the large negative number is make sure I'm doing this right. Large negative number. Yeah, okay. E to the energy over kT goes to 0 because for any, if you plot out e to the x, whatever x happens to be, negative e over kT in this case. Where the exponent equals 0, where this crosses the y-axis, that value is 1. As you go to a larger exponent, larger positive exponent, this blows up. But as you go to more negative exponent, this approaches 0 asymptotically. Okay, and that would be true, by the way, for every energy. I mean, if you're dividing by something close to 0 here, it doesn't matter so much what the energy is in the numerator. You've got this very large negative number, and it forces all the probabilities of all of the microstates, relative probabilities, close to 0. And then the partition function approaches 1. So, for high temperature, for low temperature, Z approaches 1. And the system wants to be in the ground state, is what that means. Let's see here. Yeah. You're getting run the contribution from the ground state to it. For high temperature, the partition function is bigger, and you have probabilities of being in these higher energy states. If all the energies were to be shifted by a constant energy, so if the ground state were something other than zero and you shifted all the energies up by the same amount, it would not change the partition function because you would have, the way that we use it, that extra term would cancel out of the ratios that we use in problems, in the probability ratios. Okay. Next, I want to get to how we use the partition function to calculate probabilities. How we use these probabilities to calculate the average value of the system, the average energy of the system, the average magnetization, or whatever. So this is a practical value for these probabilities. Okay, section 6.2, average values. Okay, recall the probability equation I just put up there. Probability of being in a microstate S is equal to 1 over the partition function times e to the negative energy over kT, and we're going to use a shorthand. Beta. We're going to use the Greek letter beta, which we'll define as 1 over kT. Nothing special about it. It's just because we're going to be interested in what the temperature is doing. We might take some derivatives. And that being in the denominator makes derivatives a little bit messier. So we're going to use beta as a shorthand for 1 over kT for that. As temperature goes up, beta goes down, and vice versa. Okay. This means then that the partition function is equal to the sum over all microstates S of the Boltzmann factor, e to the minus beta times the energy of the microstate S. New way of writing it, it will simplify it off. If we want to find the average of some property of the system, let's say the average energy of the system, and for, let's say, a two-state paramagnet, maybe we want to find the average magnetization, things like this. We can do, we're going to take what's called a weighted average from statistics. If you have more chance of the system being in one macro state, one energy state, versus another, then you need to weight by the number of ways it can be in that macro state. So, let's say we use a capital X. I'm putting serifs on it to make it clear that it's a capital, but I might not carry that through when I'm trying to write more quickly. If I'm interested in X, whatever X is, something I can measure about the system, like the energy, magnetization, whatever, the average X, that bar over it means we're taking the average, the mean. The average X of that system is sum over all microstates the value of the sum of the value of X for that microstate times the probability of it being in that microstate. This is the definition of a weighted average. You add up the value for that microstate times the probability of it being in that microstate for all the microstates. where the probability is given by this. Well, since we can put P in as 1 over Z times the Boltzmann factor, then when I put that into the equation for the weighted average, I can pull out the 1 over Z. It's the same for every term. One over Z times the sum over all microstates of X of S times the Boltzmann factor for that microstate S. Okay, this is the equation we're actually going to use in practice. This is the definition of a weighted average. This is a more practical version to use. Let me go down just a little there. Okay. Now, averages can be added up. So, if we have, let's see, I need to move the camera again. Let's say if energy, E bar, is the average energy of each atom in the system, and N, so let's see here. Let's say all the atoms in the system, I average over all their energies, and I get E bar. So I've got that for the system, and the system has N atoms, then the system's total energy is just the sum of all of their average energies in times. It's the sum of all of their average energies added up, which is just that would be the total system energy. So knowing the average is really useful because you can find the total property of the system from the average of its parts, of its property of its parts. And there's a trick. If you want the energy of the whole system, you can take one particle at a time, one atom at a time or molecule at a time, and treat the rest of the system as a reservoir. So if the system has some well-defined temperature, all right, then you go through one particle at a time, find the partition function, and if you've got a system of identical particles, of course that makes life easy. Treat the rest of the system as a reservoir. And you can do this then, once you've got that, you can find the system's whole energy or other property, total magnetization, whatever, very easily. Okay, there's a special case. If we're interested in the average energy, this only works for energy, it doesn't work for magnetization or other properties. There's a special equation for finding that. The average energy of the system is equal to, or the particles in the system, is equal to minus 1 over the partition function times dz by d beta. So negative 1 over the partition function times the change in the partition function with respect to 1 over kt beta. Like I said, using beta rather than 1 over kt can make it easier when you need to take a derivative. we can still use the general equation for the average value of some property of the system when we want to do the energy, but this is often easier. Okay, and keep in mind as well that by the property of derivatives, this also turns out to be negative partial with respect to beta of the natural log of z. If you take the derivative of natural log of z times -1, you wind up with that there. So there might be a case where that would be useful to you as well. All right, and in the next lesson, we'll be applying these equations to paramagnets. Let's see, paramagnet, and to the rotation of diatomic molecules. But the derivation of both of those is a little bit longer than I can get into now.